All right, hello to everybody watching this live stream. So this is going to be a working session, kind of brainstorming about experimental implications of our models. And we've thought a little bit about this before, but this is really a working session trying to understand things. So I think it's worth characterizing what, there are different categories of things. So there are what we might call theoretical predictions. There are what we might call new indications, by which I mean phenomena that we didn't think would exist, but which the model suggests exist, but we don't know at what scale and so on. Then there are, I would say, well, if we can get them, scale-independent phenomena. And then there are things which are scale-dependent phenomena, and then we have specific parameters and things. Okay, what do we mean by each of these? So, for example, when it comes to scale-dependent phenomena, we clearly have, one major scale that we have to deal with is the maximum entanglement speed, which we don't know the value of. We have some estimates, but we don't have a good, value for that. And that will determine a bunch of things. So maybe we should start off talking about, well, let's just start listing a few bits and pieces that we kind of already know. So in terms of new indications, we've definitely got dimension change. We've definitely got Oligon-like particles. Neither of these do we know how much there is of it. I think we don't know. I mean, what do we think about CPT invariance and violations of CPT invariance? I don't think we have, since we don't have intrinsic. Okay, I mean, another indication is, well, of course, the major indication is discreteness of space. Another piece then would be corrections to Einstein's equations. Nobody else is saying anything, so I'm getting very, at least Jonathan. Jonathan will definitely has things to say here. Can anybody hear me?
Yeah, we can hear you.
Okay. Okay. There's another set of questions are non-particle excitations and structures.
Anything about cosmology? Cosmological constant, something like that?
Yes, but the question is, see, the question is, what do we need to know to be able to compute the cosmological constant? That's going to be a scale-dependent phenomenon, at the very least. Maybe that's even in specific parameters. I mean,
also the dimension change is arguably a cosmological feature.
Indeed. But so let's list out what we can think of in terms of dimension change. So, for example, one recent thing I was thinking about is, propagation of photons from the CMB, from the cosmic microwave background, in a changing dimension space, in a changing dimensional space. So the question is, if we saw a photon that had been propagating since the CMB, because those are the oldest photons we have, what effect would it have if the dimension of space had changed? So, for example, clearly, clearly we can measure. Okay, so we can measure, inverse square law on very large scales. would be one example. And, we would expect the inverse square law would change to something that depends on dimension. But I don't know whether we'd observe that because it's, it's still in a changing dimensional space. So the other thing would be, okay, so an example here would be a dimension change domain wall, which probably doesn't exist, but then so I mean, well, let's scale dependent phenomena. So it depends on the maximum entanglement speed. But for example, clearly there's quantization of mass, etc. Quantization of mass, lifetime, all those kinds of good things will be quantized. But the scales are just way different from what we currently know them to be. I mean, the most accurate mass measurements are maybe 10 digits these days. Okay, that's an interesting thing mentioned by Nick here, talking about causal set theory and oscillations of the cosmological constant. Okay, so that's a good example. Yeah, that's a good, interesting question. Is time dependence of the cosmological constant. So, for scale independent phenomena, the things that we've talked about are things like photon correlations near a black hole, yeah, I mean, the problem is, what we got to think about are things where this new structure of the model suggests new things you might look for. In other words, i.e., new things to look for with unknown scale. Right, so we don't have any idea whether, for example, proton decay should happen, because that depends on structure of particles and so on. So, well, let's talk about here. Let's try and get something specific where somebody else can say something other than just me. Black hole collapse in the presence of with zeta less than infinity. Okay, so let's consider that case.
I was thinking something qualitative could be also whether magnetic monopoles are allowed.
Yes, that's a possibility. Well, let's see. Well, maybe to get things going, let's see. There's been a whole bunch of discussion about axion-like particles.
Right.
Right. I mean, so things we know, there's a lot of things where we can ask for, I mean, there's questions about scattering. Well, okay, so another question is sort of phase changes in the early universe and so on. I mean, there's a whole bunch of stuff with, early universe dimension change. but let's I mean, clearly all the particle masses, but that's specific parameters, right? So I mean, that's particle masses, all that kind of stuff, all the details about gauge groups and so on, but that's not what we're looking for here. What we're looking for here is, different kinds of experiments that I mean, another one is the ultimate, okay, so could we measure expansion in branchial space? We can measure expansion in physical space by looking at redshift. What is the analog in branchial space?
Is that a rhetorical question?
No, I was hoping somebody other than me would say something.
Isn't it just quantum speed up from QIT?
Well, but how do you measure that?
By comparing against the analogous classical algorithm.
Yes, but that's not an easy experiment to do.
Why not?
Because, okay, well, so this is, expansion branchial space would be the comparison of quantum computing to classical. Okay, let's talk about the practicality of doing that, right? So you think you've got the best possible quantum computer, and you do. So let's be very specific here. So let's say we use Shor's algorithm, for example, okay? And we're going to do Shor's algorithm, and so let's say we make the best Shor's algorithm quantum computer, okay? And then we measure what is the nominal quantum speed of Shor's algorithm. It's log n, basically. Is that right? Is that right? Shall I look this up?
No.
Is that not correct? What is correct?
I think it's log n squared log n log log n.
Okay, what's the leading piece of that?
That is the leading piece.
Tell me it again.
Log n all squared.
Okay, so it's on the order of log something or other. Okay, so say, okay, so it's which is some polynomial in log n. Is that correct?
Yeah, I think so. That's the gate complexity, at least.
Okay, so then do repeated measurements. How does the time increase? Nominally, it's some polynomial in log n. Okay, but the question is, what does it actually do? Right? But that's not an easy measurement, because what you're doing is you're saying, what's the best, what's the sort of best measuring device that I can use? See, that's one of the confusing things is, how to measure things accurately. Like LIGO, manages to measure distance to a fraction of the diameter of an atom, right? And I don't know how that's finally done. I mean, I know back in the day, in the late 70s, those guys were obsessed with quantum non-demolition measurements and avoiding the uncertainty principle in being able to make accurate measurements. Does anybody know how that works?
Well, I think the main thing in LIGO is having an interferometer with very large arms, kilometers.
Sure.
And
well, but that's because you want the total difference in I can zoom this a little bit more. I don't want to zoom it too much more, but that's because you want the total difference of distance to be as large as possible. So the gravitational wave comes through and the arms wiggle, and you have an interferometer. I don't even know what they use, what frequency of light they use for the interferometer.
Don't remember.
Right. So another thing that we had new indication is again, I mean, one of the things that will be the most bizarre indication is an asymmetry in the cosmic microwave background, but I don't believe in that. I mean, I just don't think, okay, so very early universe anisotropy. There's a thing of cosmological tests of causal sets. I don't understand why propagation. Let's see. I'm not sure that this is necessarily super relevant, though it should be. Actually, this is we should here, somebody's thesis, somebody was pointing me to. So this is variations of lambda, basically. I don't know, why does causal set theory imply variations of lambda? Let's see. Oh, come on now. Okay, yes, obviously that's the case. I mean, obviously there are quantum fluctuations in the structure of space-time, but we know that. I mean, that's kind of, what's this? Ultramassive black holes at high redshifts. Okay. Yes. Primordial lithium 7, but so what's the point? There's a change in lambda, which changes the expansion rate of the early universe. And then you could do all kinds of things. Okay, so that's an interesting question. Effects on nucleosynthesis from dimension change. Again, I mean, and there's questions, I guess, about okay, so this is giving bounds for a point particle propagating in a stochastic space. I would assume, I'll take a look at what so that's LP over LK. Okay, so we should be able to estimate. All right, so that is an interesting possibility. All right, so this would be in a change dimensional space. There's also pure discreteness, right? So there's also propagation of photons in discrete space. So it's worth remembering the highest energy photons are about, the highest energy cosmic rays are around 100 joules, right? That's oops, what happened here? Oh. Let's see, 100 joules. Convert that to electron volts. Okay, more or less that's right, 10 to the 21 electron volts. So it's worth remembering that that's for high energy protons, right? And I think photon energies, I don't know what the highest energy photons. Anybody know? Jose, do you know what the highest energy photons are?
No.
So let's see what I am. So it's 10 to the
Some
minus
sort
26.
of gamma radiation, right? The highest ones.
Sure. Well, I think the highest energy ones will come from, my guess is that they're generated by, protons are much easier to get to higher energy because they get accelerated in the Fermi mechanism for cosmic ray acceleration. They get accelerated by magnetic fields. So we've also got propagation of protons in discrete space. And so that corresponds to about 10 to the minus 26. That energy corresponds to about 10 to the minus 26 meters. Compton wavelength. So obviously that's, relative to our 10 to the minus 90 meters, that's a huge difference. So the question is there any way to take if you have a thing propagating in a discrete space, how can you detect essentially, is there, oops, why did I do this? Sorry, is there essentially shot noise from the discreteness? I think maybe we have too few we have real physicists here. Come on, physicists, speak up.
I'm reading here an article from last summer, saying that the collaboration of Chinese and Japanese astrophysicists have reported the highest energy photon ever seen with 450 trillion electron volts.
450 TeV. Okay.
Yes. And so that corresponds like 72 microjoules.
Yeah, right. Wait a minute, 450 TeV, you said. Okay, so that's 4 times 10 to the 14 electron volts. So it's much lower energy than the highest energy protons, right? Which is what I would expect. Does it say where that came from? How do we know it was a photon?
The Crab Nebula.
How the hell do they know it was a photon at that energy? Because in the detector, it's going to turn into a bunch of crud. They must have, actually, they might have done it with a coincidence detector where they have a magnetic field, but even at that energy, the deviation from the magnetic field will be low. Right, that's the question. Go ahead.
If it's the same article that I was reading, cosmic rays from protons would contain a higher number of muons than what they detected.
That sounds like, I understand the process. The process will be in proton-proton interactions, you'll have a high multiplicity of pions, which will decay to muons. Whereas in a photon interaction, you would think you have largely a cascade of electron-positron pairs.
Right. So they had water tank detectors that were specially set up for muon detection.
I see. So, all right, so we got reasonable energy particles propagating through the universe. What, I mean, for example, at around, I thought it was 10 to the 20th electron volts, you start getting scattering off the cosmic microwave background of protons. But that's still, I mean, the question is there any effect that you can expect to see that comes from, you know, the particle is propagating in a background? I mean, you know, can we model that of propagating in a background space-time that, I mean, I think it's going to be tough. I mean, I think that that's a tough thing to observe. I wonder what else they have to say here. Distance between space-times, okay. Great. So what? What can we measure from that? Yeah, okay, great. That's actually something we haven't looked as much at as we could, is distances between space-times. Discuss, distant, blah, 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 blah. Okay, nothing too exciting here, it looks like. I mean, it looks like a nice, perfectly good thesis. It just doesn't tell us a great answer to the question of, is there an obvious, let's see. Inhomogeneities, yes. Yeah, so I mean, these baryon acoustic oscillations, those are basically part of the story of non-uniformity in the cosmic microwave background, which I don't think we did. We list that here? Well, both of these things, both discreteness in space-time and dimension change, could have an effect on all right, should we turn to a different area? I mean, I think we can figure out a little bit more about the actual physical consequences of these things. Okay, let's talk about corrections to Einstein's equations. So we believe that these are of order, presumably, of order distance, elementary distance over scale size. Is that right, Jonathan?
That depends on what you mean.
Well, the order of magnitude, when you do the expansion to find corrections to Einstein's equations.
The order distance to the -2 in 4 dimensions.
Sorry, say that again?
The coupling constants are of order distance to the -2.
Well, so that would suggest it's this thing squared.
Yes.
Okay. So let's call this quantity, I don't know, let's call it kappa or something.
But more generally, it's distance to the 2- dimension.
Okay. Okay, so here's a question. Can there be a logarithmic term? Could there be a logarithmic term? Because otherwise, this, you know, in other words, in log kappa, from some, you know, tower of you know, in other words, if you sum a bunch of corrections, you could imagine that you get a series in kappa that is, you know, that sums to some kind of log kappa type thing, like in renormalization group sums of various kinds. And that would be, I mean, otherwise here, you're not going to see much until your scale size is of order the elementary distance, right? The question is there a place where you see, I mean, clearly, okay, let's talk about singularities for a second, okay? Do these corrections imply the non-formation of singularities? Okay, Jose, do you have any comments on this?
I was thinking about evaporation. So this most promising case I can think here is criticality of black holes. So very, very small black holes and how these corrections could affect them. And
well, you're talking about small black holes that have naked singularities. Is that right?
yes, close to have them. So in the limit of being zero size, that would be a naked singularity. But I can imagine that physically, the naked singularity is never going to happen, but it might have happened that the very small black holes have been formed or should have been formed, and whether these corrections could have altered that.
Right, but so the main issue is, okay, the lack of, okay, when you're forming a Schwarzschild black hole, for example, let's imagine there was something that prevented the actual singularity at the origin. Would it make it any difference? Presumably the PDEs would say there's an event horizon formed. The rest of the metric is pretty much the same. At the center of the black hole, you don't get the kind of curvature singularity that you would normally expect, but otherwise it doesn't really matter. Do you think that's correct? That's what I would assume.
Well, so I guess your question is whether a modified general theory of general relativity could alter Penrose results so much as to prevent the formation of a singularity. I don't know.
Right. Okay. So the question is, what happens to the singularity theorems?
Right. Exactly. Because these theorems contain much geometry in the sense that some results are purely unavoidable just geometrically.
Yes.
Like perhaps a black hole without a center is like a circle without a black hole without a singularity is like a circle without a center. It's just a geometrical impossibility. But
yes.
I don't know whether that is so strong as that.
Well, so the question is, do the corrections imply an effective equation of state, even for the vacuum? Jonathan, do you have a sense of that? Do you have a way of thinking about that?
I have several comments that may be relevant.
Please.
So there are these objects called echos or MECOs in conventional general relativity, magnetospheric eternally collapsing objects, which are a sort of an alternative to the singularity model of black holes. They were proposed by Mitra, I think, in the late 90s. And the way that they work is you have an energy momentum tensor whose structure halts gravitational collapse before trapped surfaces can form. Mm-hmm. And so you can evade the Penrose-Hawking singularity theorems, but still have an object whose geometry resembles that of the Schwarzschild geometry.
I see. So, okay. So this is, so CF.
So if you had, so I mean, a physical
MECOs?
MECOs or ECOs, MECOs.
Okay, with weird bouncing equations of state.
Yeah, so if you imagined you could have something where you have a collapsing star, but the photon pressure eventually halts the gravitational collapse, so you get some radiation outside the Schwarzschild radius.
Yep.
The thing you get still, from a large scale resembles the Schwarzschild solution, but it doesn't.
That's exactly what I would expect. It's exactly what I would expect. Doesn't make any difference. It's still going to, the force of the geometry or whatever is large enough that it doesn't, it won't affect the event horizon. It might affect the singularity at the center, but
Jonathan, these things do not have horizons, right? They are like super compact things.
They don't have genuine horizons. That's true.
what do they have instead?
They have things that, well, yeah, they don't have any kind of horizon.
Right. So these are like, if you have a very, very compact neutron star, it's something that right out of the object, you have a metric that looks very much like Schwarzschild, but there's never horizon and therefore never singularity.
Nothing weird happens to your null world lines at any point.
Right. So if we looked at black hole mergers today, and they were really of these compact objects, what differences will we expect?
Probably the gravitational wave signature will be rather different.
Why? What does the gravitational wave signature depend on?
Well, the ring down phase would definitely be different, because that does depend on certain small scale properties of the interior, I think.
All right. So the claim is, okay. So we're talking. Let's talk about, okay. So like the ring down phase of after a black hole merger.
Right. But I mean, we don't really have particularly good techniques for simulating that even for ordinary black holes. So
let's talk a little bit about the physics of that. Okay. So the ring down is basically dissipation associated with the emission of gravitational waves. Is that correct?
Right.
And that simulation is done how?
Sorry, I'm a bit lost here. So for example, it's possible to distinguish the collision of two black holes from the collision of a black hole and a neutron star, because they produce different patterns of gravitational waves.
Okay. In what way?
They're just different shapes. So these things are simulated numerically with codes that can evolve black holes and neutron stars, etc. And you plug in the equation of state, and in principle the black holes are unique, but the neutron stars are not. So the use of a different equation of state leaves a mark in the gravitational wave.
Okay,
and these
so
things have been collected, so they're catalogs.
So the equations of state. Okay, so the question is, a neutron star has a ring down that depends on its equation of state.
But I would say that the actual phase of the merge is the most dynamical one. The ring down, once you have a black hole formed, the ring down is just a property of that black hole, the mass it has, etc.
I understand, but just to take the naive question, the basic physics question, okay? If we look at the ring down of a neutron star, which would also happen, right? That depends on what quantities of the neutron star does it depend on? It must depend on the various Young's modulusi type things, right? It depends on the stress strain relations for the neutron star, among other things, and it presumably okay, this is a naive question, but in a neutron star, right, you can heat the neutron star, whereas in a black hole you cannot do that. Is that a true statement? That is, in a neutron star, in principle, if you start deforming a neutron star, there can be dissipation of that deformation, by internal heating of the neutron star, whereas you can also, dissipate that heat by radiation, by gravitational radiation. But in a neutron star, okay, so there's a naive physics question, right? So, I mean, if you have a deformed neutron star, presumably it can radiate heat, actual photons, and it can just heat itself up. And it can also radiate gravitational radiation. Whereas in the black hole case, I'm just trying to understand the basic physics. So I mean, the basic physics must be a neutron stars can emit photons to lose energy if they're deformed, but black holes cannot. So that must be the most basic change. In black holes can only emit gravitational radiation, presumably.
Right.
Now that's an interesting question in our theory. Is it true that black holes would only emit gravitational radiation? That's an interesting question. Right, because in standard general relativity, let's think about this for a second. At the classical level, without h bar and so on, see, the problem is there's a big can of worms here, because as soon as we're talking about discrete spacetime, we've effectively got something like h bar in there. We're no longer talking about. But the question here would be, could black holes emit oligons, for example? Jonathan, your thoughts here. I mean, there's a causal, in this causal graph, if there is indeed an event horizon, one would think.
What's the question?
Can black holes only emit gravitational radiation?
Well, if the question is, can oligons cross causal event horizons, I believe the answer is no.
Yes, but the question is there any other? So if there is a causal event horizon, for example, okay, could they emit, dimensionons? The answer is yes to that, right? There's nothing that stops them changing the structure. Well, okay, when a black hole emits gravitational radiation, how does it evade the crossing of the causal event horizon? How does the gravitational radiation also not have the constraint that it can't cross the causal event horizon? The answer is because what's happening is it's being emitted outside of the event horizon, right?
Exactly. Yeah. It's the exterior space-time that relaxes.
Right. So anything that has the quantum numbers of space-time is in principle emittable outside of the event horizon, even in vacuum, right? So
right. There's this famous saying that anything that can be radiated will be radiated.
Well, right, but anything with the quantum numbers of the vacuum, i.e. 0 plus or whatever, spin parity 0 plus or whatever else, could be radiated outside a black hole. So then the question is, are there excitations in the, we might call any excitation of the vacuum a gravitational wave. Any classical excitation of the vacuum a gravitational wave. But for example, it's not obvious to me that if there are, what about the oligon case? I mean, since we have no idea what the quantum numbers of such things are, that doesn't help. Right. Actually, this is an interesting point, that if we have more structure in space-time, right? Okay, so let's talk about gravitational waves, actually. What features? Okay, here's a question. in corrections, okay, the corrections to Einstein's equations will presumably not affect gravitational waves. I think we did this calculation before, except when their wavelength is small compared to the elementary length, or is comparable to the elementary length. But, you know, for example, okay, I mean, one thing we don't really know is what the, you know, what are the classical excitations of our spacetimes? Right? What are the kinds of, you know, it's a question, sort of, I don't know where we had this, but okay, maybe Jonathan or somebody else. I mean,
I still have several comments on the previous.
Please go ahead. More to say, the better. Yeah, go on.
Well, so in terms of dimensional radiation, unless I'm very much mistaken, this would involve extending or modifying the no-hair theorem, because effectively what we'd have to do is include dimensional mass, whatever that is, as one of the exclusions. Because the way I would generally think about it, as to your question of how it is that gravitational radiation can escape, the way that I prefer to think about it is you're basically saying when you have a black hole merger, the mass isn't escaping, so to speak. All that's happening is you're converting some mass into gravitational binding energy. Right.
Yes.
And so that there's an equivalent, there's some kind of dimensional binding energy that is the analog in the dimensional radiation case. That, as I say, requires us modifying the no-hair theorem.
The no-hair theorem is hanging by a thread. I mean, let's be realistic. The no-hair theorem has definite hair to it, so to speak. It's not. I mean, maybe Jose can say a little bit more about that. But I mean, the claim, you know, well, so one question would be, what if the black hole wasn't? I don't even know exactly what this means. What if it wasn't precisely a four-dimensional black hole? In other words, you know, that this would be non-4D black holes. What would that mean? It would mean that somewhere associated with the black hole solution is something not purely in four-dimensional space. For example, what if the interior of the black hole was seven-dimensional, let's say? Is that possible? You know, we have solution in high-dimensional space. Go ahead.
At least in some solutions, which come up in supergravity theories, in 5 and higher dimensions, you have structures which are not just spherical, but you also have this notion of black rings.
Right.
Black holes and black rings. So
right.
in supersymmetric solutions, you do have other such structures.
Right, I know. We have black Saturns and things like that.
That's right. That's right. And coming to the point of the no-hair, in some of those solutions, people try to do some procedure of singularity resolution by adding, by thinking of the black hole as a quantum foam with supergravitational corrections. Mm-hmm. I'm not sure how you would think of those. So those are usually corrections of supergravity. So in some sense, they could be related to corrections to Einstein's equation, but it's not really just Einstein. Then it is some sort of supergravitational corrections. And there you have the idea of a quantum foam. So the event horizon is not well defined. There's some kind of foaminess that resolves the singularity. And these corrections have that interpretation. So for us, the question is, do these corrections also have some interpretation of a singularity resolution?
Which and the answer quite possibly is yes.
Yeah. And then that would link to the idea of, is there something more than just the classical hair?
I see what you're saying. So you're saying, well, okay, so the issue is quantum foam has nothing much to say about the classical hair. But okay, here's a question I don't know the answer to. In supergravity theories, there are, okay, I don't know how broken the supergravity theories are. Are there massless superpartners? There's the Gravitino, the massless superpartner of the Graviton, right?
Yeah.
what does that do to these solutions? First of all, why is the massless superparticle? Is it in fact massless, or does it have some supposedly spontaneously broken symmetry?
So I don't know if they give it mass by doing some kind of symmetry breaking process. I would have to check that.
I strongly suspect they do, because I strongly suspect they're embarrassed that we don't see gravitinos.
Yeah.
So, generally, I'm they are called gravitinos, aren't they?
Yeah, yeah. So you have the classical solution, and then you have higher order loop corrections, and then you have like the one graviton correction, two graviton corrections, etc.
Okay, so the claim here, which I consider rather random, is that if the gravitino has a mass of order TeV as opposed to zero mass, oh, here's a question. Here is a question. Okay, so then, there's also, and these are supersymmetric black holes. Okay, here's a question. Does the graviton have a mass if there's a higher order correction to Einstein's equations? Does the graviton have a mass? In other words, i.e., should the gravitational potential really be a Yokoa potential? I.e., in other words, do you believe that these higher order corrections lead to a non-zero mass, essentially do they lead to a mass gap for gravitational waves? Right, because that's what you'd expect if it's a massive particle propagating rather than a massless one. Any thoughts on that, Jonathan, or anybody else?
Well, yeah, the higher order corrections have a term that you could interpret as a mass term in the Einstein-Hilbert action, which would converge to zero on large length scales.
Interesting. Okay, so the answer is, but that would mean, well, converge to zero, it either has a mass gap or it doesn't. So you're saying, I don't understand that statement.
There exist higher order corrections to the Einstein-Hilbert action in this formulation.
Yes.
Right? Those higher order corrections have a coupling constant that is of the order length to the -2 in 4 dimensions.
Yes.
They manifest as something you could interpret as a mass term. So you would get an action that you could interpret as a massive gravitation action. But those mass terms will converge to zero as the length scale goes to infinity.
I'm trying to understand that, right? I understand. So that would mean, okay, so the most obvious version has a dispersion relation. What you're basically saying is that the dispersion relation for the waves is something like, instead of, the standard, omega, whatever it is, omega goes like some constant times k, right, which is the massless case. You're saying that would have added to it, if there was a pure mass term, it would be plus, omega squared is equal to c squared plus a mass term, right? So you're saying that in this case, it would be, you would have something which is wave number dependent, right? You would say you would have some piece here, which is of order, you say mass to the -2. So that would be, is it k to the 4th? Some correction, let's call it epsilon times k to the 4th, is that right? because it's the length to the minus, yes, this thing is wave number, right? So that's wavelength, inverse wavelength. So that's, is this the right way around? Right, you take a Fourier transform of your action to get, I mean, think about a plane wave. Okay, given your action, what does a plane wave do with your action? You can never tell with Jonathan. Either he's calculating something, or he is or he thinks he has something different to say. So, Jonathan?
No, I mean, I think that's essentially correct, what you've written.
Okay. All right. So, well, we should check that, but that seems like a reasonable. Okay. So, let's see. So this means this is essentially the propagator, right? That's saying that if we think about it in terms of, yeah, okay. Right. Okay, so sorry, you were saying something else. I diverted something else. What was the other? Please, by all means, I know we have other people here. Please do speak up. You very want to hear from other people. Maybe we have some people who are quantum people, so maybe we should talk about the quantum aspects of this. But I still want to come back. Okay, Jose, I think you were saying something here about. Well, we were talking about the no-hair theorems and the relationship of the no-hair theorems to dimension radiation. I mean, this is the other sort of big thing we have is, this is, dimension waves, so to speak, which we've never really worked out. What would they look like?
I'm not sure. It's a very interesting concept, but it's difficult to think of the geometry of this.
Well, it is, yes, because I mean, what we know is that in a network we can see what a dimension wave would be like. And the question is, see, I feel like this business about like propagation of photons in a changing dimensional space, that's absolutely computable. Let's just do that computation. Let's just figure that out right now. Okay, so what happens? A photon is propagating, and essentially what happens is normally it's an inverse square law, right? Okay, so the Huygens principle for the photon. How do I spell Huygens? I don't even know. Huygens principle, is that right? No, it's just like that. Huygens principle would then have spheres of different dimension, right? And so, for example, inverse square law would turn into, let's see, it's 1 over the volume of the sphere, right? So it's, instead of inverse square, it's 1 over the space dimension minus 1. Right? That's just the decrease of flux. Okay, so let's imagine that that's the thing. So then what we're saying is, if we have a plane wave propagating, yes, does this behave like a refractive index? Does it behave like a changing speed of light? What does it behave like? Which is the same thing. Is this effectively like a changing speed of light, aka refractive index?
So you're thinking of this plane wave traveling through a space in which the dimension is constant, but non-integer? Or is the dimension
No, that
varying
one
from
that one I'm okay with, but I want one which is where it's varying, where there's small fluctuations. It's 3.01, 2.99, varying with position.
Right, but then this concept of a sphere, I mean, the points of the sphere will be potentially at places with different dimension.
Exactly. I'm merely saying that if you imagine constructing the wavefront out of a bunch of Huygens wave, okay, you've got a wavefront, right? And you're going to propagate it forwards. You can use Green's functions, you can use Huygens principle, it's the same thing, right? You've got this wavefront. Every point of the wavefront generates a spherical wave, right? But the spherical waves will no longer be those spherical waves won't all have the same. I mean, this is where it gets a little confusing, but the spherical wave, the flux in a given the amount of flux in that spherical wave will not be the same projected into, let's say you're projecting into, I don't know, 2 dimensions or something, right? From whatever d dimensions you have. What you will get, because the sphere has more places to go or less places to go, the effective flux in your projection will change.
Right, but what I was trying to say is that this is going to be some sort of a statistical effect in which you have to average, right?
That's correct. But I mean, in look, if you go through a lump of, okay, so let's imagine there's a dimension wave. The dimension wave has a wavelength of 1 kilometer, let's say. Okay, in that case, then you're asking, what you're saying is that in that 1 kilometer where the effective dimension of space-time is 3.01, what you thought was a directed wave going in a certain direction has more directions it can go in. So less of the wave, I think, makes it out. But it's also confusing because of energy conservation. I don't understand how that works. By the way, Alison on our live stream is commenting that talking about things like Ricci flows and so on. Unfortunately, the metric is not enough. The metric is in a fixed dimensional space. There is no obvious formulation of differential geometry in varying dimensional space. And in fact, that's something that would be a really nice thing to come out mathematically from studying our models, is how to think about dimension varying differential geometry. Dynamically dimension varying. Go ahead.
The way you've described changing dimension here, isn't it looking a bit similar to what they call as warping, where there is a kind of scale function that where locally at certain scales that appear large or small, you might or might not see extra dimensions? And then there are, of course, consequences for what type of particle collisions are observed in different parts of this warped universe.
I don't know. It's a good question. I mean, so in the string theory idea where you have to have curled up dimensions, you're saying that their curling factor. Okay, so you're saying warping in string theories.
So warping doesn't have to be in string theories. It could also be just in some models of gravity.
Okay, fine. Warping in string theories, etc., might be an analog. So how does that work then? So in other words,
so I think usually what they have is a scale. So there is a classical 3-dimensional space or something, and then you have a scale factor associated to it that hides or shows up an extra dimension in certain regions of that space-time and not others. So
that's exactly what we want. Yeah.
Okay. So then it sounds like warping. Only thing there you choose some kind of standard type of scaling function. Here you didn't specify how the change would be.
What should I look up to understand how that warping works?
Well, the Randall-Sundrum model would probably be a canonical case.
All right. Let us look at Lisa's model.
So in many of those cases, when you look at it from a large scale, you might just see the classical dimensions. But when you look at the space-time more microscopically, the extra dimensions open out, so to say.
Oh, let's understand how this works. Okay, so it's only warped in the fifth dimension. Graviton's probability function. Okay. Warping the extra dimension is analogous to warping space-time in the vicinity of a massive object. Okay, great. But do they have, I mean, they don't have this idea of, they just have, you're either in this dimension or in the, I don't understand, because the usual way this works is that one dimension is just completely curled up. And you're saying that the curling radius could vary with position. Is that right?
That's right.
Yeah, that's much less interesting. Right. So, I mean, this is just saying that, I see. So, okay. So this is basically saying that i.e. e.g.
In a way, you're generalizing that idea, not to a circle, but perhaps to some more general geometry, which is position dependent.
No. It's different from that. So this is, you have d plus p dimensional space-time, right? Where the p dimensions have varying curvature. That's what this model is about, right? But this is saying something much more extreme than that. This is saying the d varies. This is not allowing. So this way of thinking about it, maybe there's some equivalence here. This way of thinking about it says when the curvature of the p dimensions is very large, right? Then effectively you've just got d-dimensional space, right? But as the p dimensions flatten out, then you can have excitations that go from the d-dimensional fairly flat space into some of those p dimensions, those additional p dimensions. So the question is, could one think about the this sort of I suppose one could. Let me think about that. Actually, this is an interesting idea. So this is saying, imagine, so what we have fundamentally is we have a V of R. You know, we have our V of R that goes like R to the D roughly. Okay. So this is saying, and that could be as a function of the starting point, V of X and R, right? Says this is the number of elements in the graph starting from the point around X, going a distance R. Make sense? So now what you're saying is, if we have, yeah, all right, okay. I mean, this is right. If we have very high curvature, it's never going to change the exponent, right? But we can still, maybe we can, okay, in p-dimensional space, right? So V of X and R would, for some values of X, it would go like R to the D plus P. Okay, well, in general, it could go R to the D plus P, where P depends on X. Well, no, that's not right. See, that's what we would want. We want this. But this model would be instead V of X and R still goes like, how does this work? I think it goes like R to the D plus P, but then it has terms. Yeah, it's got to be something like this, where that is a function of, yeah, I mean, I think I can see how this works, but there is some analogy. There is some analogy here. But I don't think it's quite right. I think it's the same thing as you can't get to an exponent by expanding in a power series. See what I'm saying? This is always going to give you some kind of power series. But I agree that I think for certain ranges of R values, you might get the same numerical values. So, okay, so that's interesting. So now that might be a way of more, but I really think it's actually not that hard to make a model in which you're literally looking at the Green's function, right? For who can figure this out? Come on, physicists here. There.
Is there any way of saying going through a region of slightly smaller or larger dimension is similar to going through a region of positive or negative curvature?
No, I think not. I think those are not, they're similar, but they're not the same thing. So I mean, it's related. It's related because the geodesics, look, if you go through a region.
I mean, the linear term must have a sign, and a sign must depend on whether the dimension is growing or decreasing.
Absolutely, right. If you go through a region, except I don't think there's a linear term. I think it's a logarithmic term. That's what, if you go through a region of differing dimension, geodesics, aka rays, will diverge or converge. Right? That's the nature of that. So the point is that what we're saying is the rays in three-dimensional space. Imagine that you have a point at the origin. It's emitting rays spherically, right? Then the number of rays hitting unit two-dimensional area is, given by something that goes down like 1/r². I mean, imagine that go from a sphere to a circle, right? You're now fitting all those rays that you would have had go out in the sphere. You're fitting them all into a circle, for example. Or alternatively, you have rays going out in a circle, and as you go to fractional dimensional space, the number of rays. So let's imagine that you keep the number of rays per unit area, where the area is a p area, so to speak, or p-1 area, constant. Then yeah, I mean, my guess is that what will happen here, and that there may be some weird thing with polarizations as well. Okay, so here's a weird phenomenon. Okay, so I've got one for you.
This almost looks like some analog of lensing,
yes,
but with respect to dimensions.
Yeah, that's right. That's right. It's something like that, but it's going to be different from lensing because I claim, and I don't understand it. I mean, it has, it's like you can't get to r to the d with a power series. Now, does that means there's some, if you try and make a power series for r to the d for small, I mean, again, I don't know what consequence this has. It has some logarithmic term, but here's a question. Okay, so it is the case, is it not, that a photon has 2 spin degrees of freedom in any number of dimensions? Is that a true statement? That the little group of the Poincare group is, or the analog of the Poincare group is always whatever it is, the E2 thingy. Anybody know? You know,
it rings a bell, but I cannot say for sure.
Does a photon always have just 2 polarization states? So clearly an electron will have a different number of polarization states in different dimensions, right?
Wait, isn't that trivially true?
What?
That it only has 2 polarizations? Because isn't the Poincare group in higher dimension, it's just a semi-direct product of a Lorentzian group and the orthogonal group, isn't it? Always.
Not for p²= 0.
Why?
The little group of Lorentz group isn't the same thing as when you decompose the Poincare group, right? It's like for tachyons. Think about it for tachyons. Okay, for tachyons, you don't even get SO11 or something for tachyons, right? You get a non-compact Lie group for the thing that represents spatial rotations for tachyonic particles. So it's not the case. I mean, yes, it does turn into a semi-direct product, but that depends on p squared, so it can't be totally trivial. Let's see, but this yeah, well, let me think about this for a second. So there's one of these things I wonder. Let's see. Let me see if Michael is available. He knows about these kinds of things. Yes, Nick is saying, wouldn't you get dimension waves by substituting the fractional version of the Laplacian in the wave equation? Yes, except that's a complicated story. And yes, I mean, this is basically right, but we don't know what the fractional Laplacian really is. We can do these propagation things in networks, but we cannot easily do them in continuum space because we don't know what the continuum version of differential geometry is. But I mean, let's just do the basic question of I think like spinors have 2 to the d over 2 dimensions, don't they? I'm pretty sure. Okay, so a massive spin 1 particle, I reckon should have what is it? D. Yes, a massive spin 1 particle, because the vector should have d polarization states in d dimensions. Do you agree? It's just a vector particle, right? So, and a tensor, like a spin 2 particle, so this is something relativists here should know. The spin 2 particle will have the number of degrees of freedom. Well, a massive spin 2 particle would have the number of degrees of freedom of a symmetric tensor, won't it? Symmetric 2 tensor, I think, because it's the. Does anybody know this?
I don't know. I don't know the relation of these things with degrees of freedom.
Could somebody just look up the did I mean, Jonathan, was I wrong here with the I mean, I think spin a half. I mean, I think that gets very funky, but I think it's 2 to the d over 2. That's the dimension of the spinor representation of SOD. Does that sound at all convincing? That's the number of components, i.e., number of components for a Dirac spinor. Okay, I've got another weird thing with dimension change, is the effect on anomalies. As in, anomalies associated with gamma 5 and so on. That will be totally weird because the anomalies depend on the fact that it's even dimensional space. Jonathan, do you have a better thing to say here about this polarization states thing, or?
I mean, I think I know the answer to the graviton question.
What's the answer?
It's 5, isn't it? The number of propagating degrees of freedom for a massive graviton.
Which is equal to what as a function of d?
Let's see.
That's the number of components to a symmetric tensor. Is that right? Symmetric rank 2 tensor.
Well, yeah, that's the part that I don't.
10, right?
Yeah, exactly. That's the part that I don't agree with. I think you're missing a factor of 2. That was the point I was making.
I can believe that I'm missing a factor of 2, but can you explain it? Explain what? Where the factor of 2 goes. I mean, do you think it's not related to the number of degrees of freedom of a symmetric tensor, or what?
I don't understand the question. You have an n plus 2 times n plus 1 over 2 for the symmetric tensor, and an n plus 2 over n plus 1 over 4. Sorry, n plus 2 times n plus 1 over 4 for the massive graviton case.
Okay, how do you derive that massive graviton result?
That is a good question.
So I didn't know that result. So I mean, I don't know.
I believe that's the result. That was my recollection, but I may be wrong.
Ah, Michael joined us. Hey, Michael.
Yep.
We are talking about physics, experimental implications of physics theories. Okay, and the question on the table right now, we'll start with how many polarization states does a photon have in d-dimensional space? I think the answer is 2. Do you agree? Do you disagree? Do you know?
I don't think it's 2. The reason being the Stefan-Boltzmann constant is depending on the dimension, and I think it counts polarizations.
Interesting claim. Okay. Let's remind ourselves of the group representation theory of the Poincare group. Right. Remember that the spin degrees of freedom come from the little group, which comes from the decomposition of the Poincare group. It's an interesting claim that the Stefan-Boltzmann constant depends on let's see, depends on the polarization degrees of freedom. Well, wait a minute. You claim that constant depends on the number of dimensions of space-time?
Yes, I know, because we implemented then in the alpha unit tables. There was once a paper about this. That's why I know it.
That it depends on the dimensions of space-time?
Yes.
Huh.
Yeah, it's either 2 or d-1, I would think.
Yes, I know. It matters a lot for our purposes, which of those it is. Because if it was d-1, then we might see some signature of dimension change. So what we're trying to work out is what effect would a spatially varying dimension have on features of the universe?
I guess the most visible one and most discussed one is probably the shape of wavefronts from a wave equation, the inner part.
What do you mean?
Like if I say something in 3D, somebody hears something, then it's quiet. Where in a 2D world, it's always loud until eternity.
Well, that's because their ear is two-dimensional.
No, because like you have I believe you have an example even in NKS for the wave propagation of say a point source in d dimensions.
Yes.
Like in 3D, there's a ring going out. In 2D, there stays a non-trivial background inside. And the same and repeats at higher dimensions, the game.
Oh yeah, I remember that. Yeah. Let me look that up, that particular issue. that's frigging weird. That is so frigging weird.
It just follows from taking Huygens seriously.
Well, okay. So what the heck does that mean in fractional dimensional space?
There must be plenty of papers on, no, forget it.
There are none.
Yeah.
I mean,
no, there are plenty of papers on fractional order Laplace operator.
Oh, what does that mean? I mean, you mean the fractional order as in fractional calculus?
Yes, correct.
Is that relevant? Probably not.
I don't think so.
What is the real origin of this phenomenon? So this phenomenon, let's see, stationary pulse here in 1D, 2D, and 3D.
Yeah, there's a paper by Don Page. Photons have D-1 dimension polarizations.
Can you send me a link to that paper?
Yep. Put it in chat.
Well, that's interesting. Okay, so that implies if you, well, very interesting. So what does that mean for a photon with that propagates through why is he talking about this in de Sitter space-time? And oh, he's got formulas as a function of D. How nice. Good work. Oh, very nice. Look at this. I don't even know why he's doing this, but it's convenient that he is. Okay, so what is he saying here? That black hole mass as a function of dimension. Okay, that has a D-2, fine. Okay, he says it's D times D-3 over 2. Graviton. That's going to lead to funky things happening. If you have dimension change, it's going to lead to funky things for polarization of gravitational radiation. Can one observe the polarization in a gravitational wave detector? You're observing the quadrupole deformation, right? Can you get the polarization direction?
I thought with LISA we will be able, if I'm not mistaken. I don't know if current ones can.
Okay. But that's the space-based one, is that right? LISA, I think, is the one with satellites, yeah? Or
yes,
not?
indeed. Yeah.
Right.
5
Okay.
million kilometers once.
Okay, so the answer is we need that. Possibly the polarization. That's how it's called, right? At least just LISA, yeah. LIGO in space. Oh, somebody put in the very good. Okay, thank you. Okay. Where do we have this? Somewhere we had gravitational wave. Well, gravitational waves. Okay, let's write down gravitational waves here. Okay, a whole paper about gravitational waves. Oh, just from last year. Gravitational waves in extra-dimensional space. Okay, let's take a look at what they have to say. All wave equations. Massless wave with an additional polarization, breathing mode, and extra waves with high frequencies fixed by the Kaluza-Klein masses. You don't say, because they're going to be extra waves because they are transverse waves in that direction associated with the higher dimensions. Okay, breathing mode. In addition to the usual cross and plus polarization of the gravitational wave, homogeneous deformation of the two transverse directions. Right. Massive dispersion relation. Yes, that's exactly what we would expect. Discrete set of higher frequencies, right, fixed by the Kaluza-Klein masses because they're basically standing waves in that direction. Well, how convenient. These guys have worked this out. Okay. Okay, massless has an extra polarization mode on top of the plus and cross modes of general relativity. The case for background with a constant warp factor approximating four-dimensional geometry. Yeah. This is what we would expect. Okay, what do they think about observability? Okay. So the claim is that this breathing mode has a different deformation geometry. Yeah, well, we have no idea what the amplitude is. Yeah, well, this depends on how big the extra dimensions are. Needless to say, it's the inverse of the extra dimensions. We already know that. It's the wavelength that's comparable to the size of the extra dimensions. Well, nice paper, though. Thanks for pointing that out. Okay. Anybody want to weigh in on any of these other ones? I mean, direct measurements of discreteness. Any thoughts about that? Actually, there is a thing. Okay, propagation, there should be, quotes, scattering from the discreteness. So what that should be of the order, I feel like I used to do this stuff all the time, this kind of physics estimate type stuff. I suppose it's been 40-something years, so I'm a little out of practice. But I think what should happen is the cross-section, right, is it should be the cross-section is of order. Oh, yes, look at this. It's of order the elementary length squared times the coupling constant, right? So if it's like the Thomson scattering cross-section, right, is the classical electron radius times the fine structure constant, if I remember correctly. Anybody know what remember what I'm talking about? The Thomson scattering cross-section? Help, physicists here, come on, help. Okay. Interesting. Okay, so look, if the cross sections are order the elementary length squared, then that means that if the coupling is 1, then that means that the distance that what you would expect is that that's the cross section. So the scattering probability let's say as you go across the universe. Let's see, how does that work? So the cross section is sigma, so it's sigma times V, right? Is the formula. Sigma times V that's the density of scattering events per. Am I making sense here? That's the change in the number density as a function of time, if I'm remembering correctly. Help, guys. Oh boy. Maybe I'm spoiled. I used to do this stuff with Dick Feynman and so on. He was pretty good at this. Come on, you guys know this. So somebody knows this. Look, you think of a tube of particles. You think of a tube, and then you're asking the question: what is what fraction of, what is the probability of a scattering event when a particle goes across the universe? If the scattering cross section, if it you know what I'm talking about? Well, we could just work it out.
Yes.
Okay, so let's say the elementary length we reckon is like 10 to the minus 100 meters. So it's 10 to the minus 200 meters squared in millibarns, in barns. It's an absurdly small number. Oh, come on. It's 10 to the minus 172 barns. Okay, let me just work this out. The formula for scattering cross section given okay. The cross section is that. Yeah. That's the volume. Time. Oh no, that's right. It's n sigma v is the number of scattering events. So where n is the number density, right? Scattering event frequency is n, the number density, which has units of number divided by length cubed times sigma times v. So I think that has the right units. That's an inverse time, right? So for any given photon, the I mean, this is telling us, what I'm trying to work out is if we see cosmic ray photons, for example, or cosmic ray protons, what's the mean free path? Okay, so what we need to know. Okay, so this is what is the mean free path for scattering from the discrete background, basically? Right, that's the question. So that is equal to mean free path is that scattering cross section I am so out of practice at this stuff. This is terrible. Oh, I see. Another thing, I know what we need. We need to know the density. That's right. The reason I'm not understanding the dimensions here, we need to know the density of objects that can be scattered from. And that density is very, very high. It's just that. So it's a little bit more complicated because we need to know the Compton wavelength for the particle and compare that to the elementary length. I think I was spoiled by doing this stuff with old-time physicists. Come on, guys, you should be able to do this. And I'm at least 40-something years out of practice.
I mean, in general, I would expect dispersion to be the most observable consequence.
Okay, interesting claim. Okay, so you say, okay, so the possible effects, scattering, possible effect dispersion. But by dispersion, you mean effectively changing refractive index as a function of frequency.
Yes, I mean basically that the speed over astronomical scales depends on frequency.
So this would be speed of light depends on frequency. So that would basically be a claim. Okay, so that I agree that as the frequency gets close to the inverse scale size, that will certainly happen. Right, because when the speed of light right, when the frequency is like the elementary frequency, like the speed of light divided by the elementary length, rather elementary length divided by speed of light, then this will certainly happen. Right, then it will certainly matter.
Yeah,
the particles
hopefully one sees something earlier.
Right, but so that would be, and so in a crystal lattice, for example, you would hit the edge of the Brouillard zone, basically, by the time you're at that point.
Yeah.
Right? So it's like CF edge of a Brouillard zone. I haven't written that word. How the heck is it spelled? Brouillard.
Yeah. No. Oh, there's another I after the L's.
I thought that might be. Oh, maybe we don't even know it as a spelling word. That's shocking. Okay, assuming I spelled it correctly, we should put it in as a spelling word. Let me check that I spelled it correctly. Oh.
The I is...
No, the I is in the wrong place. That's what I thought it was. Okay. Edge of the Brouillard zone. Okay. All right. So long before you get to the edge of the Brouillard zone, you should see dispersion. And you might see scattering. I mean, the question is whether it's just a real part of the refractive index or whether there's an imaginary part. Okay, so there's the other possible effect. I don't think you would see anything on polarization states because well, okay, so there's sort of a possible effect which is essentially birefringence of some kind, polarization dependent dispersion. birefringence. But I don't know whether you would see that. If you would see, for example, in this weird phenomenon of different numbers of polarization states for in different dimensions. I don't know about that one. All right, but let's go back to the dispersion question. Is there, the only way we'd seriously see something is if there's some kind of logarithmic tail. Because something that actually depends on, by the way, Michael, I think you might want to adjust your microphone slightly. Nick is asking, is discreteness noise even observable even in principle? Yes, for sure it is. It's like when you propagate. Okay, so here's a question. In a crystal lattice, or more in an amorphous material, so analogy, right? Propagation of phonons in an amorphous material. So what do you see there? The phonon dispersion relation starts off as just omega proportional to k, if I'm not mistaken.
Yeah, for the acoustic branch.
Right. But we're not, there's no optical, I mean, the optical branch is I don't think we have anything like that. I think we're only dealing with the acoustic branch. But okay, so what does it do as it approaches? I mean, we have all kinds of weird things, like what is it, that clap process, which I probably said very wrong. But,
no, it's pretty good.
We should have those kinds of phenomena here. Again, we don't really know because these particles are pretty big, topological excitations, but at least in a first approximation. And the question then would be, what is the effect of the crystal lattice? Okay, when omega, the deviation from omega proportional to k, what is the first order term? And what does it depend on?
Don't know.
And I think it's a nonlinear term that comes from those nonlinear interactions in the lattice. And the question is, is there a logarithmic correction term? It isn't just a power, right? If there is, well, what would it mean?
Amorphous, you mean crystalline, or do you mean genuine amorphous?
No, I mean like glass, for example.
Okay.
But I'm only saying that because I think that an actual crystal lattice will have other phenomena. I don't really care at this point. I mean, the question is, let's imagine there was a logarithmic term, right? Because again, if it's a power, it's not going to show up until you're very close to the elementary length. I mean, look, here's another thing. Yeah, this is another question, is actual cutoffs in quantum field theory. So in other words, of course, most are irrelevant because of renormalization. Right, so you know what I mean. I mean, if we look at the electron self-energy or something, nominally, we have a, log of the cutoff. But in fact, it doesn't matter because renormalization says that we can't measure that.
Another effect that I would expect, I don't have a proof right now, would be that in a normal or in a fixed integer dimension spacetime, we have a very clear coupling between spin degrees of freedom and propagation degrees of freedom. And they change with the dimensions. So we will get, at least for a massive particle, we get spin part moved over in the moving part and vice versa.
Interesting idea. Okay, so your claim there is that we might have in variable dimension space, there might be essentially rotation between physical directions and spin direction. So, for example, some kind of precession or some other weird thing.
Give or take.
Yeah. Some form of dimensional precession. Well, so if something like that happened, what you might expect, what is the polarization? Wait a minute. I see. Okay, here's an effect. Okay, which might lead to variations in the polarization of the CMB that do not track variations in the temperature. See what I'm saying? So because they would be things that were features of, I mean, you could have Faraday rotation too. So I don't know whether that, if I'm not mistaken, I mean, you can have Faraday rotation just in a magnetic field. Right. So the issue is if the photons were propagating from the lost scattering surface, then you would expect that whatever phenomena led to polarization there would be on a scale, the scale size of that would be comparable to the scale size of the temperature variations that you see from the lost scattering surface. But if there's something intermediate between there and here that is changing polarizations, then you might see, you might have there's no reason to think that the dimension variation is necessarily correlated with the scale size of the density perturbations in the CMB. Does this argument make any sense?
I think I know what you mean.
Right. So I mean, you're propagating through something nearby, fairly nearby, in a few superclusters away, so to speak, that happens to be a dimension change. I mean, we don't know whether there is dimension change. So this is just a possible phenomenon that is something we haven't seen before. So that's an interesting idea, Michael. Right, in the short time we have remaining here, this is the time where we actually invent things, because we only have a few minutes left. I don't know whether we have anything interesting to say about magnetic monopoles. I mean, certainly the Dirac string. How does the Dirac string work in fractional dimensional space? I don't know my magnetic monopoles well enough. But you guys know what I'm talking about, right? The singularity that you have to have. I have no idea how that would work. It's not even obvious to me that the Maxwell equations in odd dimensional space-time would have anything like, do they have the same form? Do they even have the same, that depends on the homotopy groups, doesn't it? The presence of a Dirac string is related to the fact that, what is it, pi2 of S1? No. What is the thing that determines the fact that a monopole has to have? I mean, it's the same reason you can't comb the hair on a tennis ball without a singularity.
The fact that S3 is not S2 cross S1.
Fact that, say that again?
But well, it's the fact that the S3 to S2 Hopf vibration is topologically non-trivial because S3 is not equal to S2 cross S1.
Okay. So that means that as we go up in dimension, that is going to be different, right? Like for it's the pi 2 that what matters? Is it the what determines? You're trying to put a vector field onto a sphere. What determines that? A vector field, it's it will be pi 1, but I don't remember it being like that. That would be pi 1 of S2. Is that right?
I mean, monopoles exist in 2D. Yeah, I think they've been experimentally shown.
Okay, but that doesn't mean. I think that those let's see what.
I think earlier this year, actually.
You know, what's really disappointing about looking up things in particle physics is what a large fraction of the time the people who wrote the papers are people that I know or knew long ago. All right, let's see. Kaluza-Klein monopoles. Oh, this is the higher dimensional. Is this the relevant thing? It seems like it's not the same thing. Monopole solution. Is this the same thing, or is this? Not sure if this is the same thing. Let's see. Pi d minus 1 of sigma. Okay, so the claim is that this would be pi d minus 1. Oops. Of, in the case of Dirac monopoles, S1. Ah, spluff. It's dumb. Oh, that's that silly problem. Maybe. So it doesn't. Don't the homotopy? Don't those things become trivial in higher dimensions somehow? Don't those vary in some weird way?
I don't think so. I think they're just different.
Right, but don't they? Okay, but the question is whether if it becomes trivial and then it wouldn't have a string. Well, anyway, okay.
I don't know.
That's another question: is whether there is some bizarre feature of magnetic monopoles in fractional dimensional space. I mean, there's another weird effect of dimension change would be things like, I mean, what happens to the hydrogen atom? Yeah, this is a good question. So, it'd be
in higher dimension it gets easier, in lower dimension it gets hard.
what about the spectrum of the hydrogen atom? What about spectral lines? As a function of dimension, what happens to the, I don't know, the Lyman alpha line or something? Oh, look, it's obvious. Wait a minute. As dimension changes, the orbital angular momentum will have a different, right? Orbital angular momentum will have different, will work differently. Momentum states will work differently. So that means that the multiplicity of spectral lines will work differently. Actually, it's very weird, right? Because as you change the dimension, right, you will see different splitting, right? So in other words, if I'm not mistaken, in SOD rather than SO3, if you have a magnetic field, for example, you will see a splitting into a different number of states. E.g., Zeeman splitting will split into different numbers of states. If I'm not mistaken. That's actually one of the better dimension. I mean, that's a is there any effect on nuclear synthesis? An obvious effect of nuclear synthesis? I bet there is. Because I bet that in nuclear synthesis there will be which nuclei are stable will vary. Because I would claim I have no idea whether even the proton is reasonable in, let's see, what happens to like the pion in varying dimensional space? Because e.g. chiral that stuff depends on, it's full of gamma 5s, which have a tremendous dependence on dimensionality. I don't even know how. Yeah, I'm sorry. This is I'm realizing this stuff all. Yeah. Anyway. There are all kinds of questions here about hypergraphs and the monster group. We do not know any relation between those at this time, but that doesn't mean there isn't one. Well, okay, we should probably wrap this up. Okay, this was good, guys. I did more of the talking than I'd hoped to, but and we didn't manage to talk about things like this, which this is really the most interesting thing, is scale independent phenomena. Where we can get oh, Michael, you put some other things in here. What are these?
The last one is the hydrogen, and the other one is 2D quasi-particle monopoles from May of this year.
You are always up to the minute. Is there a stable hydrogen atom in higher dimensions? A very good question. Okay.
Even the question must be formulated, even what do we mean by this? Like by the Coulomb potential, do we mean the kernel of Laplace, or do we mean 1 over R?
No, we mean the Laplace kernel, because it's obvious that if you just change the dimension of the the propagator stays as 1 over k squared or whatever, the momentum space propagator is going to stay the same. Otherwise known as, it'd be crazy to change. Okay, so this is, if they've got Laplacian, and then the V of R is V of, a different 1 over, R minus 1 over R to the D minus 1.
I mean, it depends also on the sides of the different dimensions.
Well, yes, but that doesn't, that's talking about the curvature in different dimensions, right? We're talking about something where you have, I mean, that's a good question, is how the curvature relates, but we don't, we don't know that. All right, we didn't talk about oligons and oligon decoupling in the early universe and so on. Look, the main point here is there's all kinds of stuff. There's a big long list here. And I think this list, I think we've only surfaced about 20% of what there is. And so I think, again, the things that will be of most interest are the things which are scale independent, but which I bet there are more. I bet there are things that are sensitive to the relationship between branchial space and physical space. See, Einstein really lucked out with gravitational magnetism. How did that, does anybody know that history? Maybe Jose knows that history, right? So people had not considered, I mean, in the bending of light around the sun, there is a Newtonian value for that, is there not?
Yes, half of the true one.
Right. But the full value comes because there is gravitational magnetism as well as gravitational electric. And how was that figured out?
I don't know. I think the standard interpretation is the spin 2, is the fact that there is a 2 in the Einstein equations. That makes things twice what you would expect.
Which 2 in the Einstein equations?
Yeah, so the Einstein equations can be written as
oh, you mean the half RG mu, the half?
No. That half is there to correct the trace. So the Einstein equations are G equals twice the T mu nu, or sometimes they are written 8 pi because they add the 8 pi. But there is a 2 there, which is interpreted as spin 2. I mean, there might be an interpretation like what you say, in terms of.
No, but actually, Jonathan, I'm now curious what that 8 does in D dimensions. We must have that same 8.
So the 1/2 is dimensional dependent because it's there to correct the trace.
Yeah, right. So it's 1 over D minus 1 or something. D minus 2.
Yeah, D minus 2, exactly. But the 2 in front, I think that's dimension independent because it's always spin 2.
It probably depends on the definition. I mean, that 8 is just that's just a units thing, isn't it?
Well, the 8 is twice 4 pi. So the 4 pi is just a dimensional thing.
No, I understand that, but isn't it like rationalized electromagnetic units and weird stuff like that, where you can move around the 4 pi's and put in permittivities of things like that?
Exactly. It's like
you must be able to do that.
Yes. So the Newton equations has G, and the Coulomb equation it has a 1 over 4 pi. So it's that 4 pi, which is in the wrong place in the Einstein so Newton should have been G divided by 4 pi, and then.
I see. So the only issue is comparing with Newtonian gravity. But you could do the exact same thing with the insanity, maybe Michael can just give us a short exposition of the electrodynamic units issue. What is the 4 pi versus the epsilon 0 and so on? How does that, electrostatic units versus whatever, what is the basic point there? And does the same thing happen with gravity?
I don't know if the same things happen with gravity.
So I think the key point here is that when you have laws of 1 over r squared, it's nice to put a 4 pi in front, because that's where it comes from, right? It's the area. So it should be 1 over 4 pi squared, r squared. And so the Coulomb law does that. It's 1 over epsilon sub 0 times the products of charges divided by 4 pi r squared.
Yeah, but the reason there's an epsilon 0 there is
it's a constant. It's a constant. I mean, you could call it capital K sometimes. It's called. But my point is that Newton's law should have been written the product of masses divided by 4 pi r squared times a constant.
Yeah.
And so then the Einstein's equations would be just G equal to T. But now it's, sorry, capital G, the Einstein tensor, should be 2 times the gravitational constant times T. But now it's 8 pi.
Yeah, I get it. Yeah, okay.
Because G is missed.
But why is there a 2 there? You're saying the 2 comes from the spin degrees of freedom of the graviton?
It's a spin 2.
Weird.
Yeah.
But so how did Einstein know that?
He didn't. He just had to match things on one side and the other side.
Oh, he was trying to match Newton's equations.
Exactly. Yeah.
And therefore, go ahead.
No, in order to get the Law speed, Law gravity limit, you need that too in the Einstein's equations.
Right. But so in d dimensions, how many degrees of freedom are there in the graviton?
Well, this is a discussion we had before. These things are difficult to count, and gravity is especially difficult because there are gauge freedoms and.
Yeah, I know. So the claim was d times d minus 3 over 2.
Right. So that's the number of non-transverse elements of the tensor.
Mm-hmm.
And so, yes, but counting degrees of freedom in gravity is always difficult because it depends on whether you are using a Hamiltonian method, Lagrangian method, if you're counting gauge degrees of freedom or not, how many coordinates there are. It's complicated.
Right. All right. Well, sounds good. Okay. Well, we should wrap up for now. There's clearly more to talk about here. Well, that was fun, I thought. All right. Well, thanks to folks here and thanks to folks on the live stream. And we should probably wrap up here. Okay. See you all later.